Hello, everyone. I hope all of you are good and well. In so far where we are in the course, we have seen the definition of communication, and we have find out what is communication and why signals and systems are important for us as a communication engineer. So this is what we have seen in the previous lecture. We understand that signals are very important for us as a communication engineer or as a student in principles of communication course. Now, because signals are very important, so we started our serial number 1, which is all about signals and some fundamental concepts in communication. So we started what are signals, different classification of signals, analog and digital signals, some common type of signals, and we focus somehow on energy and power. So in the last lecture, we have seen different classification. We saw some problems about energy and power. So the take home for you is you should understand how you can find out whether a signal is an energy signal or a power signal, and how you can solve some simple problems. So there are many problems which are available in textbooks, which are also part of your assignment. Some of these problems you will solve in the tutorial as well. So this is where we stand now in this course. Now in this lecture, we will talk about frequency domain concepts, which I am sure you are all very familiar from signal and systems. You already understand what is frequency domain, what is time domain, and what are the different concepts which are related with frequency domain. So we continue our discussion from where we left in signal and system. With a quick revision, I just give you very brief idea about the frequency domain again, just to refresh your memories, and then we will move it from there. Part of our serial number 1, which is fundamentals of communication systems, and I call it simply frequency domain, or some fundamental concepts about frequency domain. Now before we start with frequency domain, just to refresh very quickly your memory about the Fourier, means what is Fourier theorem, or Fourier series, or Fourier transform. As most of you already know very well, Fourier is the name of a scientist. He was in France between 1736 1830, and he made a means discovery, I don't know what you call it, discovery, invention, whatever you want to call it, but it is something which is very important for maths as well as for engineering. In fact, most of the stuff what we have in today's world is dependent one way or other on this discovery of the Fourier. Now what Fourier discovered, initially he said any periodic signal, and when we use the word any, it means any shape. The only condition is it's a periodic. So any periodic signal, and you know very well what is mean by periodic, a signal which repeat itself. So any periodic signal, which means any signal that is repeating itself, is actually a combination of sinusoids with different frequencies, amplitude and phases. So what he told us, the Fourier, which we call it now Fourier theorem or Fourier series, Fourier simply says like any shape that is periodic, it can be written, or it is a combination of a large number of sinusoids. And how large, he normally says it's infinity. In some cases it is less, but it is in general, any periodic signal is a summation of an infinite number of sinusoids of different amplitudes, an, bn, and different frequencies, n, f naught. And what is this n, f naught? He says n, f naught, they are, n is an integer, so n is an integer, so it simply means there is one frequency, f naught, and this f naught is the fundamental frequency of your signal, fundamental frequency of a signal. And then in your signal there are multiple frequencies, and all these frequencies are n, f naught. N, f naught means integral multiple of fundamental, integral multiple of fundamental frequency. In fact, as you know that very well, I am sure all of you remember this, that there is only one signal that has one frequency, and that is sinusoid. So other than sinusoid, all the other signals, they can be decomposed, or they can be break into a number of sinusoids. And sinusoid means these two words, they are use interchangeably frequency. So whenever I say we have a frequency, it means I am saying we have a sinusoid, because sinusoid means frequency, which has of course a different amplitude or certain amplitude or certain phase. But frequency, only sinusoid is the signal that has only one frequency. So when I say a signal contain multiple frequencies, it means simply a signal contain multiple sinusoid, or in other words, if I add them all these sinusoids together, then I will get my original shape back, which simply means, let's say just for the sake of argument, I have a periodic signal something like this. Let's say this is my x of t, this is my t. You can use any amplitude a, you can use any timings here, 1, 2, whatever, doesn't make any difference. Now in this signal, it is a periodic signal. So according to the Fourier, this signal can be written as a summation of sinusoids. Summation of sinusoids. And all these sinusoids have different amplitudes, which we call Fourier coefficients, a naught, a n, b n. This is, as you know, this is the trigonometric form of Fourier series. We have another form of Fourier series which we use in signal and system, which is exponential form. But we know that by Euler's identity, e to the power jx equals cos x plus j sin x, we can always convert anything in exponential into sine and cosine, or anything in sine and cosine into exponential. So that's the reason Fourier series have two different forms. One we call it exponential form, one we call it trigonometric form, but basically they are the same thing, so it doesn't matter whichever form you use. So according to the Fourier, this signal x of t, it can be written as a summation of sinusoid, and these sinusoids have different amplitudes like a naught, a n, b n, which are different numbers. We call it simply Fourier coefficients, and they have different frequencies, which is n f naught. So there is one frequency, for example here the fundamental frequency I can see here is this, which is the time period is 1 second. So the fundamental frequency f naught is 1 over t, which is 1 over 1, which is 1 hertz. So fundamental frequency is 1 hertz, and then there are integral multiple of this fundamental frequency, which means it might have 2 f naught, means 2 hertz, 3 hertz, 4 hertz, 5 hertz, and so on. But it cannot be have 1.5 hertz or 2.2 hertz. No, it should be integral. N is an integer here, right? So it should be an integral multiple of the fundamental. So this is what Fourier is. So to understand it a little bit better, let's say I think those of my students who was with me in signal and systems, they possibly remember this, but this is very simple. I generated using a MATLAB, and I think all of you can do it very easily as a project or as an example in MATLAB. So we have a signal. This is my f of t, and the shape of my f of t is like this. As you can see, it is not exact sawtooth, but it is close to like a sawtooth kind of signal, which is y-intercept is 1, so it is crossing at 1 on the y-axis. Now this signal, if I find out the Fourier series of this signal, if I calculate the Fourier series of a sawtooth waveform, something like this, it is 1 plus 2 sine t minus 2 sine 2t plus 2 by 3 sine 3t minus 1 by 2 sine 4t, and so on. So this is like the DC component or zero frequency, and now we start from here. So this one has one fundamental frequency, and then so fundamental frequency here is 1 radian per second, right? It is 1 radian per second, and then we have integral multiple of the fundamental. So 2 times 1 is, this is 2 radian per second, this is 3 radian per second, this is 4 radian per second. Don't forget, again, anything which is written with t is your omega. So in sine 3t, your frequency is 3 radian per second. Or if you want to convert it into hertz, then you can say that 2 pi f is equal to 3 radian per second, which means f is equal to 3 over 2 pi hertz. So you can always convert from hertz into radian per second or radian per second into hertz. And this term have 5 times of fundamental is 1, so 5 radian per second, and so on. So this is the Fourier series, and these are the Fourier coefficients. So this is my let's say a naught, this is my, let's say, a1, this is my a2, which is -1. This is my A3, which is 2 by 3. This is my A4, which is -1 by 2, and so on. So what we can see is, what we are trying to see here is Fourier series in action. So we can see we have the Fourier series, and what I want to show you, that if I am, these are all also called, as you know, that these are also called harmonics. So these are all my harmonics, and this is my fundamental frequency. So you have a fundamental frequency, in this case here 1 radian per second, and then you have harmonics. So what I am trying to show you here is this signal. I am just trying to show you, if I am adding all these terms, then you will see I will get this signal. So this shows us very clearly that yes, by adding all the component in your Fourier series, you can get your original signal back. So let's start plotting one by one. So what I did is, I just consider first term of the series, which is 1. So if I plot 1 versus time, it will be something like this. So this is of course time here, and then I plot the first two terms. So I plot now, let me change the color. So let me change the color of the pen, I think, just because otherwise it is confusing. So now I am adding first two terms, 1 plus 2 sine t. So 2 sine t, you can plot it very easily in MATLAB, and then you can add 1. So whole thing will be shifted on y-axis at 1. So this is 1 plus 2 sine t. And then you can plot the first three terms of your series. So when I plot first three terms, which is 1 plus 2 sine t minus sine 2t, then my shape will be like this, and so on. So now I add first four terms of my series, which means I added another term here. So 1 plus 2 sine t minus sine 2t plus 2 by 3 sine 3t. So you can see, when I am adding more and more term, I am getting closer and closer to the actual shape of the signal. When I adding 5 terms, you see I am even more closer than the actual signal. When I adding 6 terms, so here you can see, when I add the first 6 terms of the series, I am almost very close to the actual signal f of t. So it means, by adding more and more component, and you can see it is going on. So by adding more and more component, you are getting closer and closer to an actual sawtooth waveform. So it means, I simply say that this is my signal f of t, and this has this can be written, this can be break into a large number of sinusoids, or in other words, I can say that this is a signal which have a large number of frequencies, and all these frequencies are integral multiple of a fundamental frequency, which is 1 radian per second in this case, right? So this is about what we have about the Fourier series. So in simple wordings, according to the Fourier series, we can say that composite signal is a term which is normally used. Composite signal simply means non-sinusoid. Non-sinusoid. Why non-sinusoid? I call it composite because sinusoid is the only signal, or sine wave is the only signal that has only one frequency. So anything that is not sinusoid, it is a composite signal, or it has more than one frequencies. So for example, let's say if you have this signal, it is a periodic signal. As you can see, it is a periodic signal. This is a period, and the same shape is repeating again and again. So according to the Fourier, it can be decomposed, or it can be written as the summation of sinusoids. So for example, in this signal, if I do the Fourier series of this signal, I will find out there are three frequencies. One is f. It can be any number depending on what numbers we have here on x-axis, right? One is f, one is 3f, and one is 9f. So it means in this signal, what we can see here is this signal has three frequencies: the fundamental frequency f, the third harmonic 3f, and the 9f. And I just draw it here. So this is my fundamental frequency, and this is the amplitude of fundamental frequency. Then we have this 3f. So this is my 3f blue one, and this is the amplitude of 3f. And then we have the 9f. So this black one is the 9f, and this is the amplitude of 9f, right? So it means, in simple wordings, I can say that this signal has three frequencies. So one way to show this information is like this. So I can say that, okay, this signal has three frequencies. And what are these three frequencies? These three sinusoid. One is pink or red, the other one is blue, the third one is black. Now there is another way how we can represent this, and this is I think maybe you are familiar with and most important, and this is how we represent this. We just show it on like a plot like this, and I can say on the x-axis we have a frequency, and on the y-axis I have the amplitude. So the first frequency, the pink one, has the frequency f and the amplitude, whatever amplitude. Let's say I call it a1. So the height of this is a1. The blue one, the frequency is 3f. So on the x-axis I put 3f, and the amplitude, let's say I call it a2. So this amplitude here is a2. And the third one, 9f. So on the frequency axis it is here 9f, and the amplitude, let's say, is a3. So I just put it, this amplitude is a3. So this is another way of showing the same signal here. So one way I show it here like this, and another way of showing the same signal here like this, and this is what we call it spectrum. Normally we call it a spectrum, but the full name we call it frequency spectrum. So frequency spectrum simply means that how many frequencies are present in your signal. So either I can show you this thing, which is like the shape of the signal, how the signal is behaving or changing with time, or how the amplitude of the signal is changing with time, or I can show you this like this, the spectrum or frequency spectrum, because from the frequency spectrum we can also see very easily that there is a frequency here. How many frequencies are there? 3 frequencies, f, 3f or 9f. It means we need 3 amplitude of amplitude a1, sorry, 3 sinusoids of amplitude a1 and frequency f, amplitude a2 and frequency 3f, and amplitude a3 and frequency 9f. So this is how we can get this shape back. Of course, one thing which try to understand here intuitively means it's always easy to see any signal in time domain. So this is my time domain, and time domain by default it is always very easy for us to comprehend, to think about it. Why? Because this is the natural, how you can see the variation of the amplitude of the signal on an oscilloscope. So when you see how your signal is changing with time, this is the time domain, and this is very natural for us to understand, like how my signal is behaving on an oscilloscope. On the other hand, frequency domain or frequency spectrum is somehow in the beginning, frequency domain, it's difficult for us to comprehend or to intuitively think about it, that what does it, because if I show you this, like these 3 bars, it's very difficult for you, almost impossible to think how the signal is changing in the time domain, right? Unless you have a computer. If you have a computer, then you can draw sine with a1 amplitude and frequency f, you draw another sinusoid with amplitude a2 and frequency 3f, you can draw another sinusoid of amplitude a3 and frequency 9f, and then yes, you can add them together, and then you can get this shape back, and then you can see how the signal is behaving. But if I show you the frequency domain of a signal, it's very difficult for you to understand. It's almost impossible to visualize how the signal is behaving in time domain. So that's the reason why most of the time we find out, oh, it's very hard to think about how the signal is behaving in time domain, right? It's not easy, it's difficult. One thing which I really wanted to highlight here is that all the real signals, as you know, they have positive frequency and they have negative frequency. Mathematically, of course, there is a negative axis, and then we have negative f a1, we have negative 3f here with a2, and then we have a3 with negative 9f. But for the sake of simplicity, we are not sketching here the negative side of the spectrum. As a communication engineer, honestly speaking, most of the time we are interested in the positive frequencies, but it's important for you to really understand that yes, always there is a negative frequency as well. That's why your signal is a real signal. If it has only positive frequencies or only negative frequency, then it's a complex signal. It's not a real signal, right? We will talk about it later on. Now this is the diagram which I get it from one of the lectures from Professor Raj, and it's very nice, interesting diagram. The reference is here. I think you can even watch like the whole video on the YouTube. It's very interesting diagram which gives you very clear idea about what is the frequency domain and time domain. Now try to visualize, because here I need very good visualization from you. Visualize like this, that just imagine that you have these three sinusoid, right? One sinusoid is like this, the blue one sinusoid is like this, the green one, which has a different frequency, and one sinusoid is this yellow green one, and one sinusoid is this yellow one. And as you can see, all the three, the blue one, the green one, and the yellow one, they have the different frequencies. How I know that they have a different frequency? Very easy. First of all, you see this is the frequency axis here, right? This is the frequency axis here, and one has low frequency, which is here. This one has a higher frequency, green one, which is here, and the yellow one has even more higher frequency. And we can also see easily, because their time periods are different, right? So their time periods are different, or the duration of one cycle of each of them is different. So it means all of them, they have different time periods, and because they have different time periods, so they have different frequency. Now first of all, think about it. This person here, this person here, who are looking from this angle, who are looking from this angle. So forget about this guy. Just think like this, that you are sitting here, and you are watching from this angle. So when you're watching from this angle, then you can see this amplitude axis here, and then you can see this axis here, which is the frequency axis. So you can watch only amplitude axis and frequency axis. And what you can see here, then there is a line here, right? And this is a yellow line, blue line. So you can see a blue line here, because you cannot see how this sinusoid is changing with time, because this time axis is hidden to you. So you are just seeing from here, so you can just see line. So you can see the amplitude, so you can see like a bar, you can see an amplitude, and you can see this value here, which is a frequency. Then you see another line here, right? Because all this change which is changing with time, it is completely hidden to you. So you can just see only this line here. So it means you can see the amplitude, and you can see this frequency. Let's say I call it F2, and let's say this is F1. And the third line you can see here, again you can see a yellow line, which is, let's say, at frequency F3, and it has certain amplitude. So what you can see from this angle, you can see these blue line here, this blue line, you can see this green line, and you can see this yellow line only. So this is the frequency domain, or from this guy, he is seeing only the spectrum of the signal, or frequency spectrum of the signal, or he is seeing only the frequency domain. Now the same thing, think about it, this guy, everything is the same, but now the guy who is watching from here, he cannot see this axis, he cannot see this frequency axis altogether, he cannot see this frequency axis, right? So what he can see is, he can see this amplitude axis, which is here, and he can see this time axis, which is here. Just try to visualize, you are watching from here. And this guy, let's say guy number 2, this guy number 2, or the person number 2, this is, let's say, person number 1. So person number 2 cannot differentiate this F1, F2 and F3, because for him F1, F2, F3 overlap. So all these three sinusoids are overlapping each other, and he can see some shape like this, and that's all. So this person can see only some shape like this, and that's all. So he cannot see. So this person is seeing the time domain. So this is like, we can call it, this is the time domain, and the other person is seeing the frequency domain. So this is the main point here. So this is very interesting slide, because what this slide is showing us, that time domain and frequency domain, they are same thing. There is no difference between time domain and frequency domain, right? So keep in mind that the time domain and frequency domain, they are the same thing. No difference. The only difference is at what angle you are looking into it. So from the time domain, you can think something like convert it into frequency domain, or from the frequency domain you can convert it into time domain. but it's the same thing. There is no difference. It's just like from what angle you are looking into it. If you are looking it from this angle, if you are looking from here, it's a frequency domain. If you are looking from here, it's a time domain. And if you make any change in the signal, for example, like for some reason, if I remove this yellow signal or yellow sinusoid or yellow frequency altogether, then the signal will look different in both time domain and frequency domain. So any change, if you make it in one domain, it will also reflect into the other domain, right? So time domain and frequency domain, it's just the way how you look into it. Otherwise, they are the same thing. So this is the very important point here is. Now the other thing which I would like to highlight here is that so far we are talking about periodic signal. So we say like if the signal is a periodic signal, then it can be decomposed into sinusoids, large number of sinusoids, infinite number of sinusoids with frequencies which are integral multiple of the fundamental frequency, right? So this is my fundamental frequency. So this is for the periodic signal. So let's say if we have a periodic signal, then a periodic signal spectrum looks like this, and this kind of spectrum we call it is a discrete spectrum. What is mean by discrete? I think by now all of you know very well. Anybody tell me what is mean by discrete? Yes, very good. So discrete spectrum simply means that on the frequency axis you have one frequency here, you have another frequency here, you have another frequency here, but between 3f and 9f there is no frequency. So this is only for periodic signals. So if it means in simple wordings that periodic signals always have a discrete spectrum, which means if I show you a spectrum, discrete spectrum, if I show you a spectrum and I ask you what kind of signal do you think it is, if the spectrum is discrete, it means it is a periodic signal in time domain. On the other hand, the Fourier series later on in his own life, Fourier generalized it for non-periodic signals as well. Initially he proposed something for the periodic signals, and he says periodic signals have large number of sinusoid and the frequencies are integral multiple of each other, it's a discrete spectrum. Later on he find out that even if your signal is non-periodic, it means it is aperiodic, non-periodic signal, then it also has a large number of frequencies, infinite number of frequencies are present here, and in this case these frequencies are continuous in time. Sorry, not continuous in time, these are continuous in frequency. So continuous frequencies. So the spectrum is continuous, and continuous means spectrum is continuous. Continuous means, you know that difference between continuous and discrete. Continuous means I cannot count how many frequencies are there. For example, in this case, this is a frequency axis, and frequencies is starting from 0 and goes all the way up to 4 kilohertz, which is a typical spectrum of an audio signal. So this is a typical spectrum of an audio signal. So what we can say here is that this audio signal, because the spectrum is continuous, so it means this audio signal is not a periodic signal. So this audio signal is a non-periodic signal because the spectrum is continuous, and it has frequencies which are from 0 up to 4 kilohertz, and we cannot count how many frequencies are there. On the other hand, if you see here, in this case, for example, I can count how many frequencies are there. Very clearly there are 3 frequencies. Of course, you know that for discrete you can count, for continuous you cannot count, right? So here I can say there are 3 frequencies, which means 3 sinusoid, and here there are infinite number of sinusoids which we need to add them. So these sinusoids have continuous frequencies, so infinite number of sinusoids which we need to add here, and the lowest is 0 frequency and the highest is 4 kilohertz. So anything between 0 and different sinusoid and different amplitude. So concept wise it is the same thing what is true for discrete. I think to understand it's better to think about periodic signals. So concept wise it's the same concept, but now the situation is even more complicated. So you cannot of course generate these frequencies and then you can add them together like you do it Fourier series. No. And this thing we do it calculated by using Fourier transform. So this is not something new. I think here we only talked about concept and just to revise your memories. Before we go for Fourier transform, one quantity which I would like to define here, which I call it simply signal bandwidth. Now what is the bandwidth? Bandwidth of a signal is the difference between its maximum frequency and the minimum frequency. This is simply, we call it the bandwidth of a signal. I think this word is very common. You heard a lot what is the bandwidth of a signal or how much bandwidth you need and etc, etc. So it's very simple. Bandwidth is simply the difference between maximum and minimum, which means in your signal what is the minimum frequency, in your signal what is the maximum frequency, and you take the difference. This is your simply the bandwidth. So example is, for example, you have a signal like this. X of t is 5 cosine 1500 t plus 46 degrees plus 10 sine 400 t plus 10 degrees. Of course this is not a sinusoid, right? First thing, please make it clear, it is not a sinusoid. Why? Because it has two frequencies. So it is not a sinusoid, it has two frequencies. This is the first frequency of my signal, which is, let's say I call it omega 1, 1500 radian per second. This is the second frequency of my signal, let's say omega 2, which is 2400 radian per second. So the minimum frequency here 1500 radian per second, maximum is 4400 radian per second. So we take the difference, and this is 900 radian per second. So 900 radian per second is your bandwidth in radian per second, which is 900 radian per second. If you need your bandwidth in hertz, it's always easy. You can always got it. 2 pi f is your omega, which is equal to 900 radian per second. So f is 900 over 2 pi, which means 450 over pi hertz. So this is 450 over pi over hertz is your bandwidth in hertz. So bandwidth, like a frequency, it can be written in radian per second or it can be written in hertz. So in terms of practicality, of course, I think bandwidth is something which is super important concept, and I'm sure like you heard, everybody heard bandwidth quite often, most of the time in our daily life. Some very common examples is like the audio signal has 4 kilohertz bandwidth. If it is some kind of music, then it can go up to 10, or in some cases, like if it is high definition music, then it goes up to 20 kilohertz. So bandwidth is very important because we really have to see what is the bandwidth of our signal which we want to transmit, and what is the channel or medium bandwidth we have. So you will see, we will come back to bandwidth again and again, because bandwidth is something which is very, very important. After defining bandwidth, let's move on to the Fourier transform, because Fourier transform is a tool. It's a transform, or I can simply call it, it is a tool that gives us how my signal looks like in frequency domain. Now why it is important for me to see how my signal looks like in frequency domain? Simple reason is the bandwidth. As I told you, if I have a signal, any signal, let's say g of t, and I need to transmit this signal over a channel. I need to transmit this signal over a channel. Then I need to see what is the bandwidth of g of t, what is the bandwidth of my signal, and what is the bandwidth of the channel. Then I can transmit it. If the bandwidth of my channel is good enough to transmit this g of t, then I can transmit it. But let's say my bandwidth of my channel is small and the bandwidth of my signal is large, huge, then even if I transmit, everything will be lost. So bandwidth is very important tool for communication engineers, and that's the reason Fourier transform is something which is super important for us, because this is how we will find out, we can see what are the frequencies which are present in my signal. And Fourier transform, as you know, you might ask some of you why we are not doing it Fourier series, why we are doing it Fourier transform, because Fourier transform, it is for non-periodic signals, and most of the signals we have in the real life, they are basically non-periodic signals. In fact, most of the information bearing signals who have some information, they are non-periodic signals. Why is that? Can anybody answer me? Why is that information bearing signals are always non-periodic? Yes, very good. because the information bearing signals are always non-periodic because they have some new information. If it is a periodic signal, it means information may be only in one period and the same information is repeating again and again. So normally we are not interested in transmitting something periodic signals. So Fourier series concept wise is important, but for the communication point of view, Fourier transform is much more important. Now how we calculate Fourier transform, it's pretty much straightforward, very simple, and I think nothing new here for you because you know it very well from signal and systems course, that Fourier transform is an integral, which simply means that in order to calculate the Fourier transform of a signal, I need to compute an integral. And what is this integral? It is from minus infinity to plus infinity, which means everywhere. Starting from one end goes all the way to the other end, everywhere. I need to multiply my signal g of t with e to the power minus j omega t, where omega is your variable now. So what, and then I integrate with respect to t from minus infinity to plus infinity. It means the variable t will disappear, and what left is this variable omega. Now as you know, again nothing new, you know it quite well, that Fourier transform normally we indicate with capital letters. So for example, in time domain your signal is x of t, and when we put it in frequency domain, then we put it capital X of omega or x of f. So capital letter means it is a Fourier transform of a signal, and small letter means this is the time domain. And this is the notation which we use, if you remember, which is not an equal, it is two lines and two arrows, and this indicate that is a notation for Fourier transform. So this means it is a, we are talking about Fourier transform, right? So Fourier transform calculations are not too complicated, means it's simply an integral. And similarly, the inverse Fourier transform is given by g of t. If it is g omega, if you have g omega, then g omega e to the power j omega t d omega, and you divide it by 1 over 2 pi, this gives you g of t. If you have g of f, then g of f e to the power j 2 pi f t df, then it will give you g of t. So in both cases you can see they are quite similar. The difference is here you have negative sign and g of t, here you have positive sign and g of omega. You have to integrate g of omega versus omega with respect to omega, and g of f with respect to f, and then you will get g of t. So in simple wordings, Fourier transform is nothing complicated, it's quite straightforward. The only thing is you have to simply calculate an integral. Now we just take few examples of calculating Fourier transform. Frequency domain concepts. So let's say first example, I think it's a solved example in your textbook as well, example 3.1. So calculate and plot the magnitude and phase spectrum of the Fourier transform of the following signal. So a signal is given x of t e to the power minus a t ut, where a is a constant, a can be any number. So what we have to find out is, we have to find out the n plot. We have to now be careful about the wordings which is given in the question, because these wordings means you have to read it very carefully. If it says only calculate, then you just need to calculate, you don't need to plot it. But if it is a calculate and plot, then it means you have to do two things. One is calculate and then plot. So be careful about the wordings of the problem. The magnitude and phase spectrum of the Fourier transform of the following signal. Now this signal x of t, if we can see this signal here, then this signal will be something like this. Okay, and no, I think let me remove this. Let me remove this, and then I can draw it like this. So let's say these are my two axes here, and this is t and this is x of t. Now one thing which you notice here, there is a u of t, so it means on the on the negative t there is nothing, it's 0. So it starts from here and then it goes like this. So this is, and this point, can anyone tell me what is the value here when t equals 0, then it should be, yes, e to the power 0 is 1, so this will be 1, and it is decaying with the rate e to the power minus a t. Because of u of t, this point here is all 0. So this is my signal. Now this is a decaying exponential signal, as you can see here, and we have to see how this signal looks like in frequency domain. How many, for example, if I ask you how many frequencies are present in this signal, we don't know. We never know unless we can calculate the Fourier transform of this signal. So as you can see, Fourier is very handy. If I want to transmit this signal on a channel, I have absolutely no idea how many frequencies are present in this signal, right? So in that sense, it's very important for us to really find out how many frequencies are present in this signal. Of course, I can see it is a continuous sine signal, it is an analog signal, and is it energy or power? Very good, yeah, it's an energy signal. We all know about these things, we can calculate its energy, etc, etc. But how many frequencies are there, we don't know. It's not a periodic signal, so it means its spectrum should be continuous time spectrum, right? It's a non-periodic signal, so we have to use Fourier transform. Now let's first calculate the Fourier transform. So Fourier transform, we can calculate it simply by using this. So it's x of t, so it means x of omega minus infinity plus infinity x of t e to the power minus j omega t dt. This is the definition. So simply by calculating using the definition, we can calculate the Fourier transform. I think I just maybe zoom out a little bit, and I show you how we can plot it. So this is how it looks like in time domain. So this is how it looks in time domain, right? Now we will see how many frequencies are there and how it looks like in frequency domain. So it's very simple. What you need to do is, your signal x of t is e to the power minus at ut. Now because of u of t, this lower integral limit becomes 0, upper will remain plus infinity, and x of t will be e to the power minus at, and this e to the power minus j omega t dt will be as it is. So this will be your x of omega, right? So this will be your x of omega. So this is the equation. I think now I will zoom out a little bit. So this is my x of omega. I put x of t here, and because of this u of t, this becomes 0, and this u of t will be gone. Why? Because u of t is saying that from minus infinity up to 0, my signal is 0. So it means I remove u of t and put the lower limit 0, so it starts basically from 0. If we don't have a u of t, then we have to integrate it from minus infinity. So that's the point of having u of t. So e to the power minus at, e to the power minus j omega t dt, these are both exponential, so we can add their powers. I think this is more or less like a mathematics. So e to the power minus a plus j omega t is 1 over minus a plus j omega, and exponential function integral as it is, it's e to the power minus a plus j omega t, and then you apply the limits 0 to infinity. So when we substitute infinity here, so 1 over minus a plus j omega as it is, e to the power minus a plus j omega times infinity is e to the power negative infinity minus e to the power t is 0, so everything is 0, e to the power 0, and we know that 1 e to the power minus infinity will be 1 over e to the power infinity, which means 1 over infinity, which means 0, and e to the power 0 is 1, so 0 minus 1 is minus 1, minus minus positive, so it's 1 over a plus j omega. Now this is your Fourier transform of x of t. So what we can see here is that we calculate the Fourier transform of x of c, which is 1 over a plus j omega. Now it is a function of frequency, which is omega. Now the interesting thing here is that we cannot get much information out of it in its current form, because you can see how I interpret it. What it is, 1 over a plus j omega means, yeah, fine, we find out x of omega, but then what? How I can find out how many frequencies are there, etc, etc. So what we have to do is, that's why in the question they ask you that calculate and then plot the magnitude and phase spectrum. Now what is mean by magnitude and phase spectrum? Then you can see very clearly here that your x of omega is a complex number, right? Is a complex number. Why? Yes, very good. Because of this j. So j is a complex number. So it means 1 over a plus j omega is a complex number, and when we have a complex number, it means we need its amplitude and we need its phase. Before we do that, I think just to quickly review your memories, for complex numbers, you know very well, if we have a complex number is normally in this form, a plus jb. So let's say this is my complex number, I call it simply x. So the magnitude of x, can anyone tell me what is the magnitude of x? Yes, very good. A square plus b square. And can anybody tell me what is the phase or angle of x? Very good, yes. Tan inverse of b over a. So this is, I think, nothing new, just to refresh your memories. So when we have a complex number, we can always find out its amplitude, we can always find out its phase. So here the amplitude and phase are very simple. So x of omega, amplitude is, I just call it mod, this means amplitude, right? So its amplitude is very simple. One amplitude is 1, and a plus j omega amplitude is square root of a square plus omega square. And the angle or the phase, so this is amplitude and this is phase, and for the phase it is x of omega. If it is x of omega is like this, if it is a plus j omega, then the phase will be tan inverse of omega over a. But now because it is in the denominator, so in this case the phase will be, phase of 1 minus phase of a plus j omega. Now phase of 1 is 0 minus phase of a plus j omega is tan inverse of omega over a, so it is negative tan inverse of omega over a. This is how we get it this here, right? Simple, because phase is like phase of the numerator minus phase of the denominator. Now phase of the numerator is 0. Why? Because it's a real number, 1. There is no imaginary term with j, so it's 0. So 0 minus tan inverse of omega over a. Now what we will do is, so we find out this is the magnitude and we find out this is the phase. So this is the magnitude and this is the phase. In communication, most of the time we are interested in amplitude, but here because it says plot both, so we will plot both. Let's try to plot this x of omega. Now before I show you the solution, I think how we can plot it, I can simply show you so I can simply show you how we do it. So this is your omega, and what we have to do is we have to plot x of omega, right, amplitude. Now the easiest way to plot this x of omega is, think like this, that 1 over square root of a square plus omega. When omega is 0, then what will happen? So omega is 0 means at this point what will be the amplitude? So when omega is 0, so 1 over square root of a square plus 0 square. So it is 1 over square root of a square plus 0 square, which means 1 over square root of a square, which means 1 over a. So at 0 it is 1 over a. Easiest way to do these kinds of plotting, in my opinion, you will find it quite useful, is always think like this, that what is the value when omega is 0 and what is the value when omega tends to infinity. So when omega tends to infinity, in this case when omega tends to infinity, or when omega is very large, getting bigger, then it means 1 over square root of a square plus omega square. So if omega is getting bigger and bigger, then it means the denominator is getting bigger and bigger, and 1 over infinity is approaching 0. So it means then it will be approaching 0 when omega is approaching to infinity. So it is this, something like this, right? So you starting from 1 over a, and then at infinity is 0, so it will take some shape and then it will approach 0 when omega is very large. Now what is this shape? We don't know. It depends on the value of a basically here, right? So depending on what is the value of a, but you don't have to be so precise here because it's just a rough sketch. Now when omega is negative, negative means on this side, it will make no difference, because you can see it's an even function, so it means exactly same things will be here on the other side. Or in other words, when omega tends to negative infinity, then here it doesn't make any difference. Negative values square means becomes positive value, so it's the same thing on both sides, mirror image of each other. So it means this is my amplitude spectrum. Now what is my phase spectrum? So amplitude spectrum, I just draw it here, right? So we already see in the above how we draw the amplitude spectrum. Now how about the phase spectrum? So phase spectrum is minus tan inverse omega over A. So I just rewrite it here. Phase spectrum x of omega is minus tan inverse of omega over A. Do the same thing. So this is omega, this is phase of x of omega. When omega is 0, so minus tan inverse of 0, tan inverse of 0 is 0. So it means when omega is 0, you have this point 0. And when omega tends to infinity, so when omega tends to infinity, positive infinity means this side, positive infinity, then what will happen? Then tan inverse omega over A tends to 90 degrees or pi by 2, because you know that tangent pi by 2 or 90 degree is infinity, which means tan inverse of infinity is pi by 2. So it means when omega tends to infinity, then tan inverse of infinity is 90 degrees or pi by 2. So it means, and we have a negative sign here, so that's why it is approaching to negative pi by 2, right? So when omega is going to the positive infinity, it will approach to negative pi by 2. It can never exceed above a negative 90 degrees or negative pi by 2. And similarly, when omega is negative, when omega is approaching this side, negative infinity, so when omega is approaching negative infinity, then negative comes out, negative and negative positive, and tan inverse of infinity means pi by 2, so it will approach positive pi by 2 or 90 degree. So this is your phase. Now look at these. Let me remove maybe these. So these things, what we can see now is the magnitude spectrum. This is my magnitude spectrum, and this is my phase spectrum. Now these are very important for us. Magnitude spectrum mainly is more important than phase spectrum. Phase spectrum is good because this magnitude spectrum and phase spectrum is simply showing me that in this signal, which is e to the power minus at ut, in this signal what frequencies I have and what is the phase of and magnitude of each frequency. So it has the 0 frequency, which is, as you can see, the strongest one. The amplitude is highest, 1 over A, which is very important. So now from the communication point of view, what we can see is that the lower frequencies have the higher amplitude. So I can see the lower frequencies have the highest amplitude, amplitudes, or we can simply say that these are the significant frequencies or significant component. So it means if I am transmitting this signal on a channel and my channel is not a low pass channel and my channel remove all the lower frequencies, then it means my signal will be severely attenuated, and then I cannot do anything. At the other end, receiving end, I don't receive anything at all. So it means in order to transmit this kind of a signal, I must have a channel which is a low pass channel, which can pass all the lower frequencies. Higher frequencies here, as you can see, higher frequencies are not problematic. Why? Because higher frequencies, the amplitude is getting smaller and smaller, and if the amplitude is getting smaller and smaller, then means for higher frequencies, even if these frequencies are attenuated, it don't have a significant change in the shape of the signal. So if I am transmitting this, for example, like this shape, maybe at the other end, if my higher frequencies are somehow attenuated, I will receive something like this. This is my received signal, right? This is my received signal. So means some frequencies are removed here, some higher frequencies are received here. It may have a small impact, but not significant, nothing significant, which means it is good. Then it means I can transmit this signal very easily here. But if my channel is not good, and if my channel attenuate the lower frequency, then it means it's a problem. Then uh, I cannot transmit the signal successfully on a high pass channel. So that's why it's very important. Then we must know, we must have a very good idea, we must have a clear idea about it, that what frequencies are important, right? So I think we stop here this signal. In the next lecture we will continue about our frequency domain discussions. We will talk about maybe some more examples. We don't take too many examples here of calculating the free Fourier transform, because I hope you understand, you can revise your notes how you can calculate the Fourier transform of different signals, which is not the main topic here, but we need to put things in the perspective of communication here.